Okay, so the rack, and that's this long gray or blue gear, has a mass of M equals 75 kilograms. And we want to know the moment M that must be exerted on the gear or the pinion here in order to lower the rack at a slow, steady speed down the 60-degree incline. We can neglect all friction, and then they tell us that the fixed motor which drives the gear wheel at O is not shown. Alright, so we can work this problem in a number of ways. I'm going to work it in a way that I think is the most easily understood by a student. And so what I'm going to do, we can draw a free body diagram of the gear, and then we can draw a free body diagram of the rack and show the forces of interaction that would occur here between these mating teeth. And so I just want to go ahead and jump down to those free body diagrams and sort of explain them. So I've separated the gear or the pinion from the rack, and I've not shown the teeth for simplicity. So when I look at this pinion, I have to pull a pin at O. So I see my pin reactions OX and OY. And I've got my applied torque M, and then where these gears come together, I would have teeth forces. And so if we think about the pinion, this moment tries to turn the pinion in a counterclockwise fashion, and the weight of the rack as it tries to slip down the incline would cause or attempt to cause a clockwise rotation around the center here at O. So I've shown that as a force Ft and Fn. So gears do have a radial component of force and a tangential component of force. So I've just called this Fn so that it's kind of thought of as normal here to the pitch diameter, and then Ft, which is transverse or tangent. So Ft is the result of the rack trying to slide down the incline and turn the gear in the opposite direction. And so we could easily go ahead and write a moment equation here for this gear, say counterclockwise positive. Some of the moments around O is equal to 0, and we would have M minus Ft times d over 2 equals 0. Okay, so this is the equation that's going to relate the torque on the gear to this tangential force that's going to result from the weight of the rack. I don't actually need to know OX, OY, and Fn for this. Fn is going to pass through the center at O and has no moment. All right, now let's look at the rack. So by Newton's third law, we have these equal and opposite forces. So Fn will reverse direction as it's applied to the rack, and then Ft, which points down on the gear, would actually point up on the rack. So you can think about this as the effect of the teeth on the gear that are holding the rack up, and they don't let it simply slide down the incline under the action of its own weight. I do have the weight component here, and I didn't show a weight component up here for the gear, but they didn't give me any information about that mass, so I didn't need to show that. And then I would have a normal force, and please note that what I've done here is just sort of show the normal force as it acts under each of these rollers. It's just really one net normal force that passes through the center of the gear where the weight is. All right, we also note the angle theta here is 60 degrees, so this would be theta. So this is 90 minus theta, and then we have the angle theta in here. And for this one, we're very interested in directions perpendicular to the rack and parallel to the rack. So instead of using maybe the standard XY, we might call this distance like an X prime direction, and then say sum of the forces in the X prime has to be 0. That way the normal and this Fn component never show up. We have Ft minus mg sine theta is equal to 0. So Ft is equal to mg sine theta, which is 75 times 9.81 times the sine of 60 degrees. And we find that Ft is equal to 637 newtons. And now that we have that, we would be allowed to substitute it into our previous expression for the moment around O, and we could write that m is ft d over 2, which is 637, and then our diameter is 75 millimeters divided by 2 to get a radius, so that m is 23.9 Newton meters. So, a good problem, 2 different objects to draw free body diagrams of. I used an x prime axis over here tilted in the direction of the rack, so I only needed to take the component of mg that pointed down the rack. I didn't need to compute Fn or the normal here, or Ox or Oy. Alright, so that is it for this problem.